Is my screen visible?
Yes, sir.
Yes. So yesterday rather, we learned how to find out reliabilities of different system configurations, effective reliabilities, given the reliabilities of individual modules. Now, before starting today's class, let us take an example. So, suppose that you are in a company and your manager lost a system diagram, and only what remains is this equation of this reliability, effective reliability. And what your manager now wants is, given this equation for system reliability, you need to derive the structure of the system. So can we try to do so using whatever knowledge that you have from yesterday's class regarding series and parallel uh, mm, systems? So before that, can somebody of you tell me the effective reliability of a system, effective reliability of a system consisting of two components having reliability R1 and R2, or say both having reliability R, and they are connected in parallel. They are in parallel. So what do you mean by a system being in parallel? Somebody of you, what do you mean by a system being in parallel?
Means
Sir,
like
all
if
of them have to fail if the system has to fail.
Yes. So parallel means all of the components have to fail for the system to fail. So then what was the argument based on which we determined the effective reliability? What were the steps in determining the reliability?
for parallel, everything has to fail together for it to be non-reliable, and for series, at least one should be fail.
Right, right. So for parallel, how did we do? We first find out the probability of each component failing. So what are we given? We are given the reliabilities of the individual components. Given that, we first found out what is the probability of each component failing. And then we found out what is the probability of all of the components failing together, because we want the opposite of that. So we found out that, and then 1 minus the probability of all components failing together gave the reliability, effective reliability of the system. Now, on the other hand, when you are connected in series, you are saying that the system fails if any one of them fails. So what is their effective reliability? Yes.
Sir, for series, sir,
Mm,
so R square if it is 2.
R square. So product of the reliabilities of individual components. Now, based on this understanding, just based on this understanding, can you tell something about the structure of the system from this equation that is given to you? Let us say the first, you just look at the first part. Just look at the first part that I have underlined. Can you tell something about how AB and DE must be connected
So
for
A
to
and
have
B,
So
yes,
A, B are
Yes,
parallel,
parallel. We are
and
parallel.
D and E are parallel, but they together are connected in series.
Series
and
with
yes,
C
C.
is in series with them.
yes, yes, correct. Now, if you the lower part, if you look at, then if you look at the lower part, then
A and A
A and
series, sir.
D are
B
in
and A series,
series.
both are in parallel.
right, right. So then what can you say about the structure that the system might have? So when RC acts as a short, then A and B becomes parallel and DE becomes parallel. When RC acts as open, then AD becomes in series and BE becomes in series. Is this not it? Yes. Yes. Anything you want to say?
So
Hello, are you
when
listening?
RC
Yes, sir.
Mm.
when RC becomes short, we take RC
Mm.
as 1.
Mm.
So that second part disappears, right?
The second part disappears. No. RC, we don't say RC as 1.
Okay. Okay.
My point, see. When RC is working, given that RC is working, this is the probability. This, what you are saying is correct, that whatever I have, if you can see this brace that I have drawn above, that part
Yes, sir.
is for the case when RC is certainly working, but RC is not certainly working. So you need to multiply with the reliability of RC. This part, otherwise whatever you have said is correct. This part is saying that if RC is certainly working, then the probability that the system is working, given RC is working, is this part. Fine? Any
Yes, sir.
doubts? So then, but then RC is not working certainly. So you need to get to the effective reliability of the system for the case in which you have argued what happens when RC is working. For that, you have to multiply with the reliability of RC. On the other hand, the opposite happens, that this one is the case. This part that I have just separately underlined is the conditional probability that the system works when RC is not operational. Now, but then RC is not certainly non-operational. What is the probability that RC is non-operational? 1 minus RC. So you need to multiply with the probability of RC being non-operational with the conditional probability that the system works when RC is non-operational. Is that fine?
Yes, sir.
Yes. So then, if you start to draw this, how it should look, we can say that you have a block A, and then you must have a block B which is in parallel to A. And then you have a block D which must be in parallel to some E according to what the first one is saying. So if RC is a connection like this, then if RC is a short, if RC is 1, then you have something like this. Right? Something like this. Is this okay?
Yes, sir.
Yes, sir.
RC is short.
Yes.
Yes.
Yes. So then, if the second part also has to be true, so where should be RC? If the second part also has to be true, second part of the expression also has to be true, where should be RC?
In center of AB, D side.
In the center of, do you want to say here?
Ah, yes, sir.
Yes. So then you have got the result. So if I just quickly uh, draw it, so therefore what you are trying to say is something like this. What you're trying to say is something like this. Is this okay? This is what you are saying?
Yes, sir.
Yes. Fine. So then let us take the next part. Calculate the values of upper and lower bounds on the reliability of the system for the case when RA, RB, RC, RD, RE equals to R equals to 0.9. Now, to do this, let us just, because I did not give you the slide much ahead, I will just give you this as a recap as to what was our formula for deriving the upper and lower bounds on reliability. So what was our formula for deriving the upper bound on reliability? We said that to determine the upper bound, we will find out what are the independent series paths in the system. What are the different independent series paths in the system, and then we will find out what is the probability of all these series paths failing simultaneously. Because if any one of these series paths are working, then we are saying that my system is working correctly. So to determine the upper bound on reliability, we have to find out the probability, to determine the probability that what is the chance that all these series paths will simultaneously fail. And why this is an upper bound, as we said, because in these series paths many of the components are common, right? So then for this upper bound, if we go back, then what are the different paths, series paths in my system? Given
4.
that C is, say, bidirectional, I give you this as a simplistic assumption.
4, sir.
So what are they? What are the paths?
A, D, B, E,
Yes,
then A,
just
C, E.
write down.
Okay.
Just 1 minute. A, D, and then you are saying
B, E,
B, E, correct?
then A, C, E,
A, C, E, correct?
and then B, C, D.
B, C. Okay, if this is so, then what will be the reliability of upper bound on reliability of this system? Can you just quickly do it and tell me? Then I will write it. Okay. Well, then basically you understood that what we are trying to do, we are trying to find out the reliability, trying to find out the probability that all these series paths, different series paths will simultaneously fail together. None of the series paths will be working, right? So what will we do? It will be similar to the case that all these series paths are in parallel, right? So AD are in series, BE are in series. So AD is RARD, BE is RBRE, RARCRE, like this. Then we will find out the probability of each of these series paths failing. So 1 minus RARD, 1 minus RBRE, like this. Then we will multiply them to find out the probability of all of them failing together, all these series paths failing together, and 1 minus that will again give me the upper bound. Is that okay? We are not doing it basically, right?
Yes, sir, it is
Any
okay, sir.
doubts?
Yes,
Fine.
sir.
So then let us come to the lower bound. For finding the lower bound, what did we say? We said that we will find out the cut sets, the minimal cut set, the minimal cut. We will find out the different cuts in the system, and and then we will find out the minimal cut set. So after we found out the minimal cut set, product of this minimal cut set will give me the this lower bound on reliability. So what does that mean basically? We are saying that if anybody in the cut set, if anybody in the cut set fails, if anybody in the cut set fails, so what is a cut set? A cut set is 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 a cut of the system. A cut set is a set of modules, is a subset of modules in the system, which if all these modules in this cut are faulty, then the system cannot work at all. Take any cut, if all modules in this all modules in this cut does not work correctly, then the system can never function. So we are finding a lower bound. So what are we trying to find out? We are first finding out we can what will be q cut I, probability that the minimal cut is faulty. So if we are saying that a system will fail when all components in the cut fail, that means we are seeing this cut, the components in the cut, as if they are in parallel. If we are saying that all components in the cut, if it fails, then the system fails, then for a given cut, I am looking at the individual components within a given cut as if they are in parallel, right? Correct?
Yes, sir. Yes.
Right. So then what is the probability that a cut will be faulty? We will find out 1 minus of, let us say, if you let us take one cut in here, one cut, just tell me one cut, one of
AB.
AB is also a cut, correct. If both A and B does not work correctly, then the system cannot work. So then what is the probability of A and B failing together? 1 minus RA into 1 minus RB, right?
Yes.
Yes. So the probability that at least one of A and B will work is this 1 minus of 1 minus RA into 1 minus RB. Similarly, what are the other cuts in it? So I'll just jot down the cuts. So these are the paths. These are the paths. Similarly, I will jot down the cuts. You said AB is a cut. Somebody also said BE is a cut. What are the other cuts?
ACE,
Yes.
BCD.
ACE is a cut. ACE is a cut, and BCD is also a cut. Yes, BCD is also a cut. So then we are saying that what if any one of these cuts, if any one of these cuts fail, if any one of these cuts fail, then the system can never work. If any one of these cuts fail, if any one of these cuts fail, we found out the reliability of an individual cut. For example, for AB, we found out 1 minus of 1 minus RA into 1 minus RB. This was the reliability of this cut AB. Similarly, we will find out the reliabilities of the other cuts. Now we are saying that given this minimal cut set, the minimal cut set is this. This is the set of minimal cut set. Now we are saying that if any of these cuts fail, then your system will fail. So then what are we doing to find out the lower bound on reliability? We are finding out the products of the reliabilities of these cuts. Are you with me?
Yes, sir.
Yes. Okay. So with this, and then there is a small extension. You can do this at home. I will give this slide set to you. So what will be the value of the effective reliability RS for the upper bound and the lower bound when all values of reliability is equals to 0.9. Okay. So till now, we have been seeing systems in which we are saying that these are complicated systems with redundancies in different ways, in complicated ways, series, parallel, and we were finding out the effective reliability of the system. Now, if given the effective reliabilities of an arbitrarily complex system, fine, that is fine. But how do we finally find out whether the output that you have got is correct or not? Okay. So we will look at how to find out whether the answer that you derive is in a system in which the components can be, some of these components can be faulty in such a system. How do we finally know at the output that you have got a right answer or a wrong answer? So we will look at certain systems, a set of systems like this for in the next part of this class. So the first one is an M of n system. An n module system which needs at least m of them for proper functioning. So you have n components or n modules in the system. Out of these n modules, if m are working correctly, then you are sure that the system will work correctly, which means you have a system something like this. You have modules arranged like this. And you also have a voter which votes on this. This one is component 1, component 2, 3. This is the nth component. This votes. And this one is a voter which produces the output produced by M. So M is obviously somebody which is majority, means at least half of N. If it is greater than, then if it produces, suppose you have a 3 module system and you are trying to find out 2 out of 3 system. 2 out of 3 systems. So if 2 out of 3 components work correctly, then your system will work correctly. So what will the voter do? It will take the inputs, 3 inputs, and if at most one of the components are incorrect, then it will get a majority vote. Based on that majority vote, it will say what will be the output. Is that okay? Any doubts? Hello, are you there with me?
Sir, could you please repeat this?
Yes.
Explain.
So I am saying that you have n modules and you say that the system will work correctly if at least m among these n modules work correctly. So how do you determine whether m out of n is working correctly? Through a voter which votes on the outputs received from all these components. So all these components are, let us say, in parallel, and then there is a voter which receives the outputs from all these components, and then and then the voter does a majority voting or finds out which m. If there is a concurrence of at least m modules which says the answer is same, which produces the same answer. So if m out of these n systems produce the same answer, that is produced as the output of the voter, and that is the output of the system. So essentially, you can mask errors in n minus m. So if n minus m of the components are not working correctly, you can still produce a correct output in the system. You can mask that error, fault. Sorry, if n minus m are faulty, then you can still produce a correct output, and the error will not surface at the output due to that fault. Are you okay
Yes,
with
sir.
me?
Yes.
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 So now, how do you determine the reliability? See, the reliability is determined through an equation like this. What does it say? It says that what is the effective reliability? The reliability is something like this. The system works correctly when all the n components work correctly. The system works correctly if n minus one of the components work correctly and one of them is not working correctly. The system works correctly if two of the components are faulty and n minus 2 are working correctly. The system like this, going like this, the system works correctly if at most if n minus m of the components are not working correctly, but the remaining m are working correctly. Is that okay? Okay.
Sir,
So
I is going from M to N, right? So
I is going from m to n. I is going from m to n.
so that's the
So then,
lower bound. At least M are working correctly, and then we are adding up
right, right,
M plus 1 and so
right,
on.
right. So then let us dissect this equation a bit more. So then first, let us say what is the probability. So this this is NCI, right? You understand, right? Whatever is within
Yes, sir.
this bracket is NCI.
Yes, and
So so let us say what for the case in which all of these n components are working correctly. So how do you which means none of them are not working correctly. So in that case, I is equal to what? I is equals to n. When all are working correctly, then I is equals to n,
yes, correct.
right? M of n, right? So in that case, you will have r to the power nt into 1 minus r to the power n minus n. So which is 0. So essentially, when all are working correctly, then the effective reliability of the system is r to the power nt, right?
Yes, sir.
What is r to the power nt? R to the power nt is r to the power
When
nt is what?
when all of them are working correctly.
It is the probability that all the n components are working correctly. This is it. Now, then what is the probability? What is the probability that one of the n components are working incorrectly and all other n minus 1 components are working correctly? In how many ways can you have one component working incorrectly and n minus 1 working correctly?
NC1.
NC1. So that will be given by NC1 into R NC1 into R to the power n minus 1 t, right? R to the power n minus 1 t. Sorry, it is NC n minus 1. NC1 is what is NC1 is equivalent to NC n minus 1, right?
Yes, sir. Correct.
Yes. So NC n minus 1 um, into r to the power n minus 1 t into 1 minus rt. This is the total probability. This is the total probability that you have one of the components failing and n-1 working correctly. So if you take any instance, let us say out of this, the first n-1 are working correctly and the nth component is not working correctly. For that, you do not need this combination. You just need the formula will be r to the power n-1 into 1 minus rt. Now, but any one of these components can fail and the rest n-1 can be working. So you have to multiply this with nc n-1. Okay, right. So then this was the case for one of the components working incorrectly and n-1 working correctly. Now you could have two of the components not working correctly and n-2 working correctly. So if you now argue on that, in how many subsets of 2 can you generate from a set of n components? nc2 or nc(n-2), right? Right? And
Yes.
find out in how many ways can you have a situation in which two components are not working correctly and the n-2 are working correctly. Likewise, the equation will be nc n-2 into r to the power n-2 into 1 minus rt to the power 2. Okay, so this will be the case. So now you can understand that if you have an m of n system, that means at least m must work correctly. So how do you generate the effective reliability of the system? That m are working correctly, m plus 1 are working correctly, m plus 2 are working correctly, up to all n are working correctly. You just add up this total of them. So you have a summation from I equals to m to n nci r to the power I 1 minus rt to the power n minus y. Any confusion on this equation anymore? Anybody ask a question? Yes, please. Is this fine?
Yes, sir.
Yes. So here an important assumption is that failures are independent, as we did for the earlier case as well. So what do we mean by this? Failures are independent. Some failures could be correlated. Let us say, for example, how could failures be correlated? Failures of components. Because failures of components, if they're correlated, then you cannot multiply these reliabilities independently like this. Because the failure of one component means that other component has a high probability of failure. When can this happen at all? Let us say that you have this n modular redundancy, m of n system within a car or within an aircraft. Within an aircraft, you have this triple modular redundancy where you have three processors producing outputs on some input and on the same input, and you say if two of these outputs agree, you say that this is the output of the system. You decide that that will be the output of your system. Now, two of the processors are in a zone in the aircraft which has high temperature, significantly high temperature, and the other processor is in a cool temperature. So then the two processors which are at a high temperature has a higher probability that there will be some problems with the memory, there will be some the processors will get heated faster and produce an erroneous result. So because both these processors are in a zone which has high temperature, their failures are correlated, which means if one fails, the other also has a high chance of failing. But for the third system, which is in a relatively cooler place, that failure is independent. Do you get my point? What do I mean when I say failures are independent and failures are non-independent? Do you get my point?
Yes, sir. Yes,
Yes.
sir. Among the components, right, which are
Among the
understood.
components, I'm saying two of the components. Let us say these components are processors. could be anything. These components are processors. Two of the processors are in a place where temperature is very high, and one component or one processor is in a place where the temperature is low. So if one processor fails, there is a high chance that the other processor will also fail if it is in the both of them are in the high heat zone. But here in our analysis, we are assuming that such a thing does not happen. The failures are independent. Failure of one component is independent of the failure of another component. Okay. Now, a very important point is this that we did not see in this. What happens if the entire system fails due to a common point of failure? So there is that failures are non-independent. So when the failures are non-independent, that means there is a hidden component which is there. That means the heat in that system, which makes the failures of them correlated. So you cannot simply calculate as simply like this. We will not go into that analysis, but when you are doing any practical analysis or any real life analysis, you have to also keep this in mind. That is what I am just trying to point out, that this is a very fine equation. This will work given the individual reliabilities. But if they are correlated, it will not be as easy as this. But you know the mathematics, that how can you determine given the reliability in that system. Now, by the way, just one question. Can you just tell me that we are doing so much of calculations on these reliabilities? How do you at all calculate the reliability of a component? What could be the mechanism of determining the reliability of a component? We said reliability is the probability that the system is functioning correctly from the beginning of its lifetime till now. For a system, we are saying that it is not irreparable.
We have to
Yes.
test the components, I mean, after production. So it has to
Yes.
undergo certain number of tests, right?
Yes. So the values of these reliabilities are determined after, say, manufacturing test. So you create several of these components when you are mass producing, right? And then you test on all of them, go on testing over all of them. And the factory then gives you that this component that we have produced has a reliability number as this, because they are mass producing it, and for their component of this type, they will have a given reliability. And you will argue or do analysis on the given reliabilities from the manufacturers. Or if you are continuously using a lot of these components, you can also derive some reliability value. But it will be something like this. You have to generate reliability in this way. Now, what other common point of failure, given that these failures are independent, leave that aside. What other common point of failure can you have here? Can you tell me something which is very obvious?
V is a failure.
The reliability of V. So, to generate the effective reliability, whatever you have the reliability of these systems, these modules on this left side, if your V has a very poor reliability, then your output is gone, right? So then whatever you do on this side, you have to have some RV multiplied to it. The actual reliability of the system has to include the reliability of the voter, otherwise everything is gone, right? So then this is the weakest link in this system. So let us see, we'll see how to handle this, but let us go on a bit more. So this one is M of n system is a popular system. In particular, this triple modular redundancy, which is 2 of 3 system, is very popular, especially in safety critical systems such as aircrafts. So in a triple modular redundant system, in general, you have an n modular redundancy or an M of n system, where M has to be at least equals to n plus 1 by 2 to have a majority voting. So we talked about the voter already. This is what we were saying. And what we were saying with respect to that heated zone was something called correlated failures. In the presence of correlated failures, it is not so simple. The calculation is not so simple. You have to include the reliability of the system in that situation to determine the overall reliability. Okay, then, so what is the reliability of a triple modular redundant system? Can you just tell me? If everybody has a reliability of R, what is the reliability of a triple modular redundant system? What will it be? So let me just quickly write it. So that will be RV, that is the reliability of the voter, multiplied by, just using this summation, I equals to 2 to 3. So if two are working correctly, then it is fine. R to the, let everybody has a reliability of R, then sorry, you have to have this 3ci into r to the power I into 1 minus r to the power 3 minus I, right? Is this okay?
Yes, yes, yes.
Yes. So then what are we getting here, therefore? Equals to RV dot three so what are we getting?
3R
Sir, overall
square.
it RV into 3R square minus 2R cube, sir.
Right. 3R square like this, na? 3R square minus 2R cube. This is what you are saying?
Yes, sir.
Right. Right. So now if you put, if let us say the individual components have very poor reliability, R equals to 0.25. That means the probability that the system is working correctly from 0 to the current time is 0.25. How can this be? It's a very old, worn out system, very old system, no repairs, nothing. So the reliability of individual components is gone to hell almost. 0.25 is almost dead. Fine. Now in this system, what you want is that, let us say, then let us put an M of n system to make it better. The reliability to, if you may give many components, then our system should work better. So you made an M of n system or a triple modular redundant system in this case, and you found out that this is the effective reliability. Now if R equals to 0.25, what is the value of this part? What is the value of this part? So 3 into 1 by 4 square, right? Minus 2 into 1 by 4 cube. Hello?
Sir,
Is that okay?
0.15625.
Okay, 0.15625 you said? Is this what you said?
Yes, sir.
Hello?
Yes,
Yes.
sir.
Yes. I'm not calculating, but you see, the point is this, that your individual reliability of this component was 0.25, and then your effective reliability of putting so many things together, voting, etc., doing 3 components, there your effective reliability has reduced. So which means that If your individual components reliability is low, there is no use putting multiple systems together. Rather, it is all bad. It is better having a single module in that case. So now, why is this happening? Or when will this be better? Okay, for the other case, let us say that your reliability is 0.75. Then can you just quickly tell me a similar calculation and tell me the effective reliability if R equals to 0.75? R equals to 0.75. Can you similarly tell me very quickly?
0.84375.
0.84. So which means that it is very beneficial. If your individual reliability is good, then if you have triple modular redundancy, then your overall reliability is being enhanced through the system having. So there is use of having triple modular redundancy. However, if the individual system reliability is low, then making it triple modular redundant has no effect, rather it has a bad effect. So then this is the analysis. What happens when individual modules have very poor reliability? So here you have two lines. One is a 5 MR system and the other is a 3 MR, triple modular redundant system. So one is a 2 of 3 system, the other is a 3 of 5 system. So the comparison of NMR when n equals to 3 and n equals to 5 to that of a single module. So when R is below 0.5, sorry. Oh my God, why is it not? So when R is below 0.5, then the redundancy becomes a disadvantage. Why do you see on the x-axis you have the reliabilities of individual components? Here you can see when the reliability. So the exact way in which we calculate the effective reliabilities, they have calculated the effective reliabilities and plotted these graphs. So this graph plot says that what is the effective reliability, whatever we just calculated. Leave out R voter, don't put R voter in the picture. What is the effective reliability of a 3 of 5 system, and what is the effective reliability of a 2 of 3 system when for different values of individual reliabilities of the component. So when the individual reliability is 1, the overall reliability is very high. When the individual reliability is 0.9, 0.8, like this. So now it is saying that, and this simplex is the reliability of a single component, right? So it is saying that when the individual component has a reliability less than 0.5, then the overall reliability of the system reduces below the reliability of a single module or a single component. However, if the reliability of the system is higher than 0.5 of an individual component, if the reliability of an individual component is higher than 0.5, then the reliability of the overall system will be enhanced. Otherwise, the reliability of the overall system will not be enhanced with respect to the reliability of a single component. Is that okay?
Yes, sir.
Yes. So, but then reliability 0.5 is very common. Means reliability of 0.5 means what? You have a component which fails half the time. Means there is a half probability that it will work correctly. So even then you will get something. So if you have a system which is even slightly better than that you have 60% chance that this components will be working correctly, then by having triple modular redundancy, you get a boost in the effective reliability of the system. Okay, now we talk about voters. Then how we will, firstly let us see that type of voters, and then we will see how the problem of voters can be handled. So a voter, as we saw in the last diagram, receives inputs x1, x2 dot dot up to xn from an m of n cluster and generates a representative output. So what will be the simplest voter? The simplest voter will compare bit by bit of the outputs from each module and say that suppose you have two outputs from component A and component B. What the voter will do, it will component bit by bit the output from A and the output from B, and if it exactly matches, it will say that both these outputs are in agreement. Otherwise, it will say it is not in agreement. Now, however, such a system works only when the functional processors, means which generate the output, that means these components match bit by bit, right? And has to be synchronous in clock. So the processors have to be, or the components have to be identical and must be using the same software and the same digital circuit, for example, and has to be synchronous and should exactly produce the same output. Otherwise, the even correct outputs from two processors may slightly diverge, or let us say from two components may slightly diverge, at least in the lower significant bits. It could highly happen, right? The processors are producing same output, but in the lowest significant bits, last few significant bits, the output is varying. Correct? It can happen. So in that case, what we use is something called a plurality voter. So what is a plurality voter? We declare two outputs, x and y, as practically identical if mod of x minus y is less than del for some specified value of del. So we determine some small value del, and we say that two outputs are same if the difference between these two outputs, the absolute difference between these two outputs, is less than del. Okay. But then it is important to understand that this is not transitive. This relationship is not transitive. So what do I mean to say? If let us say x and y, I say that x and y are practically identical, and I say that y and z are practically identical. That does not mean that x and z are practically identical. Are you with me? Hello? Hello?
Yes, sir.
Yes. So here comes the plurality voter. So a k plurality voter looks at a set of at least k practically identical outputs and picks any of them as the representative. Now, what do we mean by practically identical in this case? Any one of these outputs must be identical to the remaining k minus 1 outputs. Any one of them. All of them will be practically identical to the remaining k minus 1. Only then will we say that you have at least k practically identical outputs. They are not transitively identical, right? And then picks any of them as the representative output. For example, let us say if del is 0.1 and you have 5 outputs, 1.10, 1.11, 1.32, and the subset 1.10 and 1.11 would be selected by a two plurality voter. So if a voter, we are saying that I have a two plurality voter, that means you need to find a subset of two which are practically identical. So you have been given 5 outputs here. You are saying you are getting 2 of them as practically identical with the bound on del to be 0.1, and therefore the two plurality voter will return 1.10 and 1.11. Is that fine? Then we shift to unit modular redundancy. I think we won't get time today, so we will see this.
Sir, 1.3 and 1.4 also.
0.1 0.1.
1.32.
So how 1.3 and 1.4, 1.32 and 1.49? So what is 1.32 minus 1.49 mod? It is greater than 0.1, right? Hello.
Yes, it's a 0.17.
Yes, so therefore it is greater than 0.1. So then
Yes, yes.
you will not get. So that is why in this case, if it has to be practically identical, it has to strictly follow mod of x minus y should be less than del.
Okay, sir.
Right? Okay. Okay. So any questions? Any more questions? Otherwise, we come to the end of this class. Hello.
No, sir, no
No, sir.
questions.
No.
No, sir.
No. Okay. So then, thank you.
Thank you, sir.
Uh,
Thank you,
thank
sir.
you. Welcome.